This is the 8th video in a series devoted to differential equations. Today we're going to look at applications of first order equations before moving on to second order equations in the next video. So we're going to quickly go through a couple of kind of basic examples before looking at what I think are more interesting examples. So the first basic example, which we won't actually do much with, is exponential growth and decay. So exponential growth and decay is talking about the change of a function being proportional to the current value of the function. So in other words, we have the differential equation y prime equals k times y. So notice the change of y is proportional to y. So that's clearly a separable differential equation, and we can solve that differential equation to get y equals y naught, which is like the initial value, e to the k times t. And we could do that using methods that we've previously seen in videos. So if k is bigger than 0, then we have exponential growth. And if k is less than 0, then we have exponential decay. That's all I'll really say about this, because likely you're pretty familiar with exponential growth and decay. So the next example of an application is Newton's law of cooling. And so in order to set up the differential equation, we need three things. So first, T, evaluated at T, so capital T, will be the temperature of some object at a time T. Then we'll have T sub m, that'll be the temperature of the medium that that object is within, again at time T. And then finally we'll take K to be some sort of temperature decay constant of whatever medium that our object is in. And so Newton's law of cooling says that the following differential equation is satisfied for the change in the temperature of our object. So notice the temperature of our object is kind of the unknown function, whereas we will know the temperature of the medium function. Okay, so we've got T prime equals minus K times T minus Tm. Okay, so let's reorganize this a little bit. So we'll have T prime plus K times T equals K times Tm. Okay, but notice that this is a first order linear differential equation for our function t. And that's because this function tm is known. So let's put that here. This is known in our setup. So let's look at a special case of this. And this special case is generally what is presented in these types of courses. So let's say our special case is the case when the Tm is a constant. So Tm is a constant. In other words, the temperature of the medium is not changing. So that would be something like taking bread out of the oven and putting it at room temperature. So the medium there would be the air in the room, and if you've got climate control, then that air is not changing temperature. So that means we've got a pretty simple separable differential equation, and it's actually pretty natural to start with our original differential equation instead of this version of the first order linear differential equation. So maybe we would like to write this as dt, where I've got upper and lowercase as necessary, equals minus k, and then t minus t sub m. So we can rewrite that as dt over t minus t sub m equals minus k d little t. And of course, I'm abusing notation here for solving a separable differential equation, but we discussed why this works earlier. Okay, so now we can take the antiderivative of both sides with respect to the appropriate variable. Over here, we'll get the natural log of the absolute value of t minus tm. And then over here, we'll get minus k times t plus some constant. And then next, we can exponentiate both sides. That'll give us the absolute value of t minus tm equals some new constant e to the minus kt, where I used exponent rules along with our standard trick of like absorbing constants. So just to reiterate, I have e to the minus kt times e to the c, but I rewrote e to the c as that capital C over there. Okay, so now let's set t equal to 0. and say that T evaluated at 0 is T sub 0. In other words, like the initial temperature. We're introducing some notation here. So that'll turn this into T sub 0 minus T sub m in absolute values equals our number C, because e to the 0 is 1. Okay, so that means our constant is equal to this absolute value of our difference. Now we can plug that back up here, and we have the absolute value of T minus T sub m equals the absolute value of T naught minus T sub m times e to the minus kt. But now we can solve this for T, and in fact what we'll get is T is equal to the temperature of the medium plus the initial temperature minus the temperature of the medium times e to the minus kt. And you might say, well, where did my absolute values go? Well, it turns out that my absolute values take care of themselves because I have them on both sides of the equation. And it all boils down to, is my initial temperature greater than or less than my temperature of my medium? If it's greater than the temperature of the medium, then we will cool off until we hit the temperature of the medium. And if it's less than the temperature of the medium, then we will warm up until we're equal to the temperature of the medium. Okay, so now let's also notice that as we take the limit as t goes to infinity, we will approach the temperature of the medium. And that's because this term right here, this exponential decay type term, will go off towards 0. But that makes sense, because if you were to like leave a warm bread out of the oven at room temperature, it would eventually get to that room temperature. Okay, so now let's look at another class of applications, which are pretty classic. They are mixing problems. So for our next example, which will be one of two mixing problems, let's consider the following scenario. So a tank initially contains 30 grams of salt, 30 kilograms of salt in 2,000 liters of water. Then water containing a half a kilogram per liter flows in at a rate of 10 liters per minute and then drains at the same rate. So our first goal will be to introduce some notation. So we'll set Q of T equal to the mass of the salt in the tank at time T, and then set up a differential equation for Q and solve it. And then our last goal will be to determine the limit as T goes to infinity of Q of T. So that would be some sort of steady state amount of salt in the tank after this whole system's been running for a while. Okay, so I've got a little picture of what's going on here. Water is flowing in, it's being mixed, and then it's flowing out. Okay, so let's notice that since Q represents the mass of the salt of the tank in time at time T, Q prime is the change of that mass, but there are two things that are changing the amount of salt in the tank. There's the salt coming in from the flow in, and then there's also salt draining out. So that means we need to consider the mass of salt coming in minus the mass of salt coming out, because that'll be the net change, those differences. Great. And so now we can calculate those pretty easily. So notice the mass coming in is equal to a half a kilogram per liter times 10 liters per minute. So in other words, it is 5 kilograms per minute. So that's just from multiplying this concentration coming in with this rate of the inflow. So here we have 5 kilograms per minute. Now let's look at the mass flowing out. So the mass flowing out will be the concentration of the entire tank times the rate that the water is flowing out. But look, it says that it drains at the same rate, the same as 10 liters. So that means we're going to need 10 times the current concentration. But the current concentration is just equal to the current mass divided by the volume. And so our volume is 2,000 liters. Notice it's always 2,000 liters because our inflow and our outflow are the same. And this is also kilograms per minute. Okay, nice. So now we can do a little bit of simplification, and that'll give us Q prime, or maybe we'll call it dQ by dt, is equal to 1 over 200 times 1,000 minus Q. So that's just from canceling this 10 and this 2,000 down to 1 over 200 and then factoring out. But when we factor out, we multiply this 5 by a 200, giving us 1,000. Now that's a separable differential equation. And in fact, we also have an initial condition. The initial condition is built into this first sentence. The tank initially contains 30 grams of salt. That means we know that Q evaluated at 0 is 30 kilograms, I should have said. So we've got a separable differential equation. We can easily solve this. So we've got dq by 1,000 minus q is equal to dt over 200. Taking the antiderivative of both sides will give us minus the natural log of 1,000 minus q equals, let's see, t over 200 plus a constant. We can maybe move this minus sign over to change that to a minus t and then absorb it into the constant. So next up, we'll exponentiate both sides, giving us 1,000 minus q equals some new constant, e to the minus t over 200, where we're using that rule of absorbing constants as needed. Now, next we can plug in t equals 0 to solve for c. So if we plug in t equals 0 to this, we get 30. So that means we have the equation 970 equals c, because e to the 0 is 0. And that finally gives us our final function for q. And that'll be 1,000 minus 970 times e to the minus t over 200. Great. So we've solved our differential equation. This will model the amount of salt in the tank at time t. Now let's also take our limit. So the limit as t goes to infinity of q of t is equal to, well, it's equal to exactly 1,000. That's because this exponential decay term will trend off towards 0 as t approaches infinity. So we get this limit is 1,000. Now let's see if that makes sense. So after an infinite amount of time, all of the water in the tank should look exactly like the water that's flowing into it. But the water flowing into it has half a kilogram per liter. The tank has 2,000 liters, so we would expect the tank to have 1,000 kilograms of salt, but that's what we've determined over here. So this checks out with what like common sense would tell us. Okay, let's look at another mixing example. Now for our next example. So a 1,000-liter tank initially contains 50 kilograms of salt and 500 liters of water. Salt water with 1 kilogram per liter is pumped in at 10 liters per minute. Then the tank mixes and drains at 5 liters per minute. So this is the main difference from our previous example. The water flowing in is coming in at 10 liters per minute, whereas the water going out is flowing out at 5 liters per minute. So that means we're gaining 5 liters in the tank every minute. So the volume of water in the tank now is changing. Then our goal is to determine the concentration of the water in the tank when it begins to overflow. Okay, so let's start by making a differential equation for the amount of salt in the tank and then take it from there. So introducing some notation, let's say f of t is the mass of salt at time t. So I'll just write it like that. And then V of t will be the volume of water at time t. So notice that V of 0 is most definitely equal to 500. That's just kind of a given. And then we can extrapolate the value of V given this difference in 5 and 10, which we'll exactly do. Okay, then notice our concentration. So let's write this down. The concentration is F of t over V of t. So that'll be an important thing to calculate at the very end because that's our last goal. So notice here, our last goal is to determine this concentration. Okay, nice. So now let's immediately notice that we can write down the formula or the equation for V of t pretty easily. So V of t is equal to 500. So that would be like the initial volume plus 5 times t. So let's talk our way through that. So notice that 5 is most definitely equal to 10 minus 5. And that would be the water flowing in every minute minus the water flowing out every minute. So that's how we get this for the volume. Okay, so now we can go ahead and write a differential equation for our mass. So we've got F prime, and so that's going to be the mass in like we had before. So notice the mass coming in is equal to 1 kilogram per liter times 10 liters per minute. So that would be 10 kilograms per minute. I'll leave the units off. And then we have that is subtracted from the mass going out. So that's going to be the concentration going out times the rate of flow out. The rate of flow out is 5. So we have 5 times the concentration going out. But notice the concentration going out is just the concentration of the tank, which is F of t over V of t. So that's going to be 5 times F over, well, we calculated V to be 500 plus 5t. So we have something like that. So notice we can simplify this a bit, given the fact that everything in the denominator here is a multiple of 5, so we can cancel that down. That gives us this nice first order linear differential equation of F prime plus F over t plus 100 equals 10. Of course, I canceled this 5 with these 5s down here, and then I moved it over so it would look like a first order linear differential equation. Okay, so now we can use our standard solution strategy for a first order linear differential equation, thinking about this term right here as 1 over t plus 100 times f of t. So that means we need our integrating factor. Recall that we called that alpha previously. So alpha is equal to the exponential of the antiderivative of this function that's in front of f. So that would be 1 over t plus 100 dt. We can take that antiderivative, and that's going to be the natural log. That gives us the exponential of the natural log of t plus 100. In other words, it gives us t plus 100 because of the way that the exponential and the natural log cancels. But now we can use our formula for the solution to our first order differential equation. Check back in a previous video if you need to see that. So that's going to be f of t is equal to 1 over alpha. So that's going to be 1 over t plus 100. That's our calculated function for alpha. Times the quantity, the antiderivative of alpha times b. So that's going to be t times 100 times 10. That's our function b in this case. So that'll be 10t plus 1000 dt plus some constant. Okay, so let's maybe make our calculation. This gives us 5t squared plus 1000t plus some constant over t plus 100. So I get that from taking this antiderivative and then multiplying this t plus 100 through in the denominator. And now we can plug in t equals 0 and recognize that we should get the number 50 because that's our initial condition. Maybe we should have written that over here. So f evaluated at 0 is 50, and that comes from this portion of our given setup. Okay, so that gives us an equation that we can easily solve for C. So if we plug in t equals 0, then this part right here cancels, this part right here cancels, and this part right here cancels, leaving us with C over 100 equals 50. In other words, C equals 5,000. Okay, so now we've got a function for f. We've got f is equal to this, where we replace C with 5,000. Okay, so let's bring that to the top, and then we'll address our final goal. So far, we've determined that the following function models the mass of the salt in the tank at time t. So we've got this nice rational function. And now look, our final goal is to determine the concentration of the tank when it begins to overflow. So when will it begin to overflow? Well, notice that the tank can only hold 1,000 liters. So to find the time of overflow, we'll set this volume function, which we discussed before, equal to 1,000. So we need the volume of T, like I said, to be equal to 1,000, but that means we need 5T to be equal to 500, just by moving things around here. That means we need T to be equal to 100. Okay, nice. So we're looking for the concentration of the tank at time T equals 100. So let's see, at T equals 100. So that's going to be F evaluated at 100 divided by V evaluated at 100 by this thing that we had up here. So, but V evaluated at 100 is exactly 1,000. That's what we got from this overflow condition right here. There's not really much that needs to be said about that. So we just need to plug 100 into F. I'll let you guys check that, but in the end, what we'll get is 31/40 grams per liter, or in other words, 0.775 kilograms, I should say, per liter. So that's our final concentration. Okay, so let's finish this video off by looking at an example of a first-order differential equation that models population. So we'll finish this video off by talking about logistic growth. So here's the basic idea of logistic growth. I'll put it in terms of population, but there are a number of systems that grow logistically. So population change is proportional to the current population, but the growth slows as the population approaches some limit. And that limit is called the carrying capacity. Okay, so how can we encode that into a differential equation? Well, maybe let's say P is the population. So population growth, or the change in population, would be its derivative, so P prime. So it needs to be proportional to the current population. So I'll say K times P. And then we need to encode that this growth will slow. In other words, this derivative will get closer to 0 as the population approaches some limit. And we can encode that as this also being proportional to something that measures the distance the current population is from that limit. And we can maybe write it like this. So this is 1 minus P over A, where A is that thing that we're calling carrying capacity, or that limit over here. So again, that limit of maximum population is known as the carrying capacity in this setting, and we'll use the letter A for that. So notice that this differential equation does it. It's proportional to the population. Look, it's something times the current population. But then it's also multiplied by this thing that gets pretty small as P approaches A. Notice if P is equal to A, then we have 1 minus A over A, which is equal to 0, and our population will not change at all. Okay, so now let's include in here an initial population. So P of 0 equals 0. Okay, so now let's solve this differential equation, which we'll do with separation of variables. So I'll write this as dP over P times 1 minus P over A equals K dt, using like standard separation of variables techniques. And now in order to take the antiderivative of this left-hand side, we probably need to do a partial fraction decomposition. So let's do the calculation of that over here. So we want to take 1 over P times 1 minus P over A and write it as something. I'll maybe call it capital X over P plus something else. I'll call it capital Y over 1 minus P over A. So that's our standard partial fraction decomposition setup. Now let's clear denominators by multiplying by this denominator on the left-hand side to both sides. That'll give us X times 1 minus P over A plus Y times P equals the number 1, because I cancel that out over here. And now I'll use the trick of evaluating this at different values of P. So let's first evaluate this at P equals A. So notice evaluating at p equals a cancels this term out. We have 1 minus 1. Then evaluating it over here, we'll get y times a equals 1. So in other words, y equals 1 over a. Next, we'll evaluate this at p equals 0. So that'll have the effect of canceling this out. Then we'll have x times 1 equals 1. So in other words, x equals 1. Okay, so that means this kind of version of our differential equation is the same thing as the version which we get from using partial fraction decomposition like that. So in other words, we have 1 over p plus 1 over a times 1 minus 1 over p minus a dp equals k dt. Now we can take the antiderivative of both sides, left-hand side with respect to p, right-hand side with respect to t. So that's going to give us the natural log of p, and then we'll have minus the natural log of 1 minus p over a equals k times t plus some constant. Here I use the chain rule and stuff in order to take the antiderivative of that second term. Now I can use log rules to put this together. This will give me the natural log of p over 1 minus p by a equals kt plus a constant. I can exponentiate both sides. That'll leave me with p over 1 minus p over a equals a constant times e to the kt. And then at this moment, I can plug in my initial condition. So notice plugging in t equals 0 will give us something like this. We have our constant is equal to p naught over 1 minus p naught over a. Okay, nice. And then we could maybe tweak this to make it look a little bit nicer. So our constant equals a times p naught over a minus p naught. So I think that looks a little bit nicer. Okay, so let's bring this equation right here with that version of c plugged in up to the top of the next board, and then we'll finally solve for p. So here's where we ended the last board. We had our population p was expressed in terms of a function of t via the following equation. And now from here, we can solve for p. Maybe we would do that by maybe first multiplying the numerator and the denominator of the left-hand side by a to simplify it a little bit. So we have a minus p like that. And then we can cross multiply and start moving some things around. So that'll leave us with a minus p naught times a times p equals a times p naught and then a minus p times e to the kt. Okay, so let's multiplying this up here and this up here. Now we can maybe cancel this a from both sides. That simplifies everything a little bit. And then we can gather everything that's a multiple of p on one side of the equation. So that'll be a minus p naught times p. And then here we'll have plus p naught times p e to the kt equals p naught times a e to the kt. Now we can factor a p out of this left-hand side. That'll leave us with p. Then we have a minus p naught, and then plus p naught e to the kt equals p naught times a e to the kt. Finally, we can divide by this whole chunk. That leaves us with p evaluated at t equals p naught times a times e to the kt over a minus p naught plus p naught e to the kt. So that would be the solution to our logistic differential equation. But one thing that I'd like to point out is this is not the standard way that we see this. The standard way that you would maybe see this in a textbook is what you get by multiplying the numerator and the denominator by e to the minus kt. And that'll leave us with a times p naught in the numerator. And then in the denominator, we'll have p naught plus a minus p naught e to the minus kt. KT. And that's what we take as our final solution. Okay, let's see an example of this. Okay, so we just determined that logistic growth follows the following equation. So we've got an initial population of P naught, some sort of growth rate of K, and A is the carrying capacity. Then P of T, in other words, the population at time T, is P naught times A over P naught plus A minus P naught e to the minus KT. Now let's just do a quick check, and if T approaches infinity, this does approach A, which is the carrying capacity, so that makes sense. Furthermore, we can check that if you start with a population above the carrying capacity, this is a decreasing function, whereas if you start with a population that is below the carrying capacity, this is an increasing function. I'll let you guys check that by maybe graphing though. Okay, so now let's say that given the population of the US in 1950 was 150 million, 1980 was 227 million, and 2010 was 310 million, let's assume logistic growth and estimate the population at 2100. Okay, so let's notice that we immediately have a population given as follows. So 150A over 150 plus A minus 150 e to the minus KT, where we're taking P of 0 to be 150. So in other words, P of T is population T years after 1950. We're setting 1950 as like our set point. Then we have two more pieces of information. We have P evaluated at 30 is equal to 227 million. And then we have P evaluated at 60 is equal to 310 million. And I guess I should say here, population in millions. So that gives us two equations to solve for capital A and our growth constant K. And I'll let you guys decide your favorite way to solve such a system of equations, but I solved it in Mathematica, and what I ended up with was A equals 515. Recall that A was the carrying capacity, so that tells us that this predicts the carrying capacity of the United States to be 515 million. And then we'll have, let's see, K is equal to 0.02. Okay, so in the end, we have our population is modeled by 150 times 515 over 150 and then plus, well, 515 minus 150. So that'll be like 365. So we have 365 e to the minus 0.02 times t. So that would be our logistic equation modeling the population of the US. And then to finish this thing off, we calculate P evaluated at, let's see, if we need 2100 and our set point of 0 is 1950, that would be P evaluated 150. And I'll let you guys check this, but what we end up with is 459 million. So that's our estimated population at 2100. Okay, so let's end this with some warm-up problems. So I'll leave you guys with one warm-up problem, and it's a mixing problem. So a 2,000 gallon tank is filled with 1,000 gallons of water and 100 pounds of salt. Then brine that has 1 pound per gallon of salt flows in at a rate of 4 gallons per hour. It mixes thoroughly and then drains at a rate of R gallons per hour. Then let's set Q of T equal to the mass of the salt in the tank at time T. And then there are two questions to answer. Find Q of T using differential equations if R equals 4. So in other words, the inflow rate and the outflow rate are the same. And then next, find Q of T if R equals 10. So that means you're gaining volume in the tank every hour. Okay, that's a good place to stop.